Welcome to the second video of our tutorial series on the Earth materials and systems. This one is going to focus on the processes that change the Earth and how they result from energy flowing through the Earth, and also how that changes the actual Earth itself, the matter in it. So, the first thing I want to talk about is this idea of energy. And energy is basically just the ability to do work. And the energy budget of the Earth depends on two main things: the sun and the energy from the core. Now, most of the processes that change the surface of the Earth are going to come from the energy of the Earth itself, which is called geothermal energy, or the energy from the heat of the core of the Earth. And let's talk about why the core is hot. By the way, geo means rock and thermal means energy. So it's rock energy, right? Therefore, the energy of the core of the Earth. Now, why is the Earth hot? It's hot because it started hot, and it has not cooled down since then. Remember, the Earth formed by collisions of rocks in the early solar system, and those collisions released a lot of energy. And so, in the first, the Earth was a big molten ball of magma and lava. And over many, many years, the outer layers cooled down to form the crust, and that is still happening. The Earth is slowly but surely, like a bun that came out of the oven, slowly but surely cooling down. Now, this process takes longer for larger planets. Smaller planets like Mercury and Mars, which are slightly smaller, but a bit smaller than the Earth, cool down faster. And that's because the surface area to volume ratio of the Earth is smaller because it has a bigger volume, right, to actually cool down on a surface area that doesn't grow as fast as the volume does. And so larger planets cool down slower. The same reason why larger animals also cool down slower and retain heat better. So that's why the Earth is still hot. But there's other reasons. It's not just that. Gravity of the Earth is large enough that it's also squeezing that core and causing it to stay hot. Smaller planets also don't have enough gravity to keep their cores hot. So the Earth is big enough that there's also a factor. But we think that the Earth would already be solid if it wasn't for a third reason, that it actually still has warmth enough to be molten on the inside. It has radioactive isotopes inside its core, which are still decaying, and because of that, they are warming up the inner layers of the Earth. So together, for these three reasons, there is energy inside of the Earth that's slowly going towards the outside, and this powers a lot of processes that are changing the Earth. Before we can talk about these processes, I want to quickly review the idea of heat transfer. Now, heat, again, is another name for energy in the process of being transferred. And there's three main processes of transferring heat: conduction, convection, and radiation. When you touch a hot stove, or you touch the handle of a pan that's sitting on the stove and you feel the heat, that's conduction. What's happening there is that hot particles are vibrating in place, and as they vibrate, they hit other particles, making them vibrate. So it's a collision between particles, which is causing the heat energy to transfer from one to the other. Convection, on the other hand, is heat transfer by movement of warm particles. So if you see a lava lamp and you see that as it gets warmed up, it actually rises up, right? Because it becomes less dense. And then it gets to the top, touches the top, conduction, releases some of that heat, and then gets colder, denser, sinks back to the bottom, hits the helium again, the process repeats itself. Now, you do have conduction at the bottom and at the top for the thing to get warmed up in the first place, or then release the heat. But in between, as the hot lava lamp blob is rising, it's carrying the heat with it. And so as the same thing happens in weather, as hot air rises from areas which are hotter to areas which are colder, the same happens inside of the Earth. We'll talk about that in a second. So convection is usually a cycle, and it has to do with the movement of hot particles. Then you have radiation. And by the way, on the stove, before radiation, on the stove, when you have that hot pan, hot water at the bottom of the pan, where it's touching the hot bottom, gets hot, rises to the top, releases the heat, sinks back to the bottom, when it gets denser, gets hot again, less dense, rises to the top, and it's a cycle. So in the example of the pan, you have that too. Lastly, we have radiation, right? So radiation is heat transfer by light waves. So even sitting far away from a heat source like a heat lamp, or the sun warming up the Earth, or the hot stove, you don't have to actually touch it to feel that heat. And that's because the infrared radiation is actually coming in through light waves and warming it. How do these processes are visible on the Earth? Well, You can see conduction because the mantle warms up the crust by touch, and the core warms up the mantle by touch. You can see convection because the magma is constantly rising and sinking in the mantle due to convection cells. And you can see the radiation because that's how the Earth loses heat to space, and also how it's heated up by the sun. Let's see that in the picture to see if it helps to make more sense. So when you look at the Earth, the core is hot, and the core is touching the mantle. So by conduction, the mantle gets hot. Then the hot magma of the mantle, molten lava, starts to actually rise as it becomes less dense, carrying the heat with it by convection. Then it touches the crust again, conduction, gets cooler, denser, sinks back down to restart the process, creating these cells of convection of rising magma plumes, sinking back down as they cool down eventually after touching the crust. So the crust gets hotter by conduction and then radiates this heat to space with infrared radiation. If you could take a picture of the Earth through infrared, it will look glowing red compared to the rest of the space around it that's super cold. The Earth is constantly emanating heat, but this is a process that's going to take a very long time to cool down the Earth due to the pressure of gravity still warming it up, and due to the fact that there are radioactive isotopes which are constantly warming up the core. So all of it together with the original heat of the Earth's formation, the Earth is still hot. And that heat is important because it powers the processes that change the Earth, many of them anyways. But there are other sources of energy which matter for the Earth, which is, of course, the sun. The sun warms up the Earth through radiation, right? And that way, the Earth gets more energy to its budget. And that is very important because it causes all the weather on the Earth, and also all life forms depend on that through photosynthesis. 99.9% of life forms depend on the energy of the sun. There are some that actually depend on the heat of the Earth. They live near volcanic vents of volcanoes and get the energy out of the chemicals coming from the volcanoes and the heat coming from the volcanoes. But most of the life on Earth depends on the solar radiation. So together, the sun and the energy of the core of the Earth make up the energy budget of the Earth. Now, if you're talking about life, the sun is definitely more important. If you're talking about weather, the sun is definitely more important. But if you're talking about geology and the process that changed the Earth, the core of the Earth is going to be one of the most important things. And the first process that we're going to be talking about are going to be mostly about that. The first one I'm going to talk about here is actually plate tectonics. So plate tectonics is this idea that the core of the Earth has heat, which warms up the mantle, and those rotating magma plumes that we talked about it 2 seconds ago cause pieces of the Earth's crust, because the Earth is broken into pieces, to move around relative to each other. And that movement causes the plates to collide with each other and cause lots of deformations to the surface of the Earth. So each process that I talk about, by the way, I'm going to talk about how it changes the matter of the Earth and what powers it, what's the energy behind it. So in this example, it was obviously the heat of the core that was causing that. But because the heat of the core has something to do with gravity, I would include gravity as an energy source for that as well. And of course, gravity is also what's pulling plates to subduct underneath others, which also helps move them. And so together, the magma plumes and gravity are causing those plates to move around. And as they move around, they're going to end up deforming the pieces of the Earth and causing changes to it. Some of those changes are also going to be caused by things like earthquakes. So as the rocks deform, they actually bend elastically. And then for thousands and thousands of years, they will store energy because they're bending. But then the plates will continue to shift until the rock can't take it anymore, and it will either crack or shift near a fault line. Fault lines are basically cracks on the surface where the rock has already cracked before. And a lot of times, rocks get stuck to each other along those cracks. And when they finally slide past each other, they're allowed to deform and suddenly release the energy they had inside. Or if they don't have a crack, they will crack and cause a new fault line. Either way, as the energy is suddenly released, deformations and cracks happen all over the Earth as seismic waves travel through it, bending it up and down. That process very clearly changes the surface of the Earth very suddenly. The energy for that, again, is coming from the energy of the core, since it's related to plate tectonics. And of course, because of that, also related to gravity. Do note, by the way, that earthquakes are possible separately from plate tectonics due to other processes like subsidence and uplift, which don't have to be because of plate tectonics. We'll talk about those in a second. Then you have volcanoes. Volcanoes are basically cracks or fissures on the Earth's surface through which molten rock called magma rises from the mantle to reach the surface, at which point it becomes called lava. Now, sometimes volcanoes don't let lava out, they just let water vapor and gases come out. But either way, it's energy coming from the inside of the earth, it's spilling to the surface. Volcanoes deform the surface because they actually make new land, right? New minerals as the rocks, lava solidifies. And they also cause mountains and uplift as they push to the surface of the earth, causing the earth to actually bend upwards. Of course, the core heat and gravity are once again involved in forming this because gravity is part of the why the core heat is round, and the core heat is clearly what's causing the volcanoes to happen. By the way, the volcanoes don't only deform the earth upwards. After they explode, they can also cause craters, which deform it downwards. So either way, the surface of the earth can be deformed by volcanoes. Speaking of deforming upwards and downwards, you have the process of uplift and subsidence. They're kind of related to each other and also related to the core heat because, as you will see, one of the main reasons why they happen is because of plate tectonics and therefore related to the core heat and the gravity of the earth. Uplift happens when the plates collide against each other and the rock bends upwards. Subsidence happens when the rocks bend inwards. So plate tectonics clearly has everything to do with that. But not only that, volcanoes can also cause uplift, and magma, as it gets hotter underneath, a magma plume is pushing from underneath, it can cause the ground to bend upwards. You can also cause ground to bend downwards because of the same kind of reason. If the magma that used to be there is no longer pushing it up, then the ground will sink downwards because of less pressure from underneath. Then you also have the changes in weight, which is why gravity also matters. If you have a new glacier that forms, the added weight to the crust will actually push it downwards. Same thing happens after a mountain forms. It would actually, yes, the mountain uplifts it, but then the weight of the mountain will push down the crust, causing it to bend downwards. This is why continental crusts are so thick, because as they form both upwards and downwards in bending of the earth. Then you also have situations where you have less weight, say a glacier melted or a mountain eroded. Then you're going to have to remove weight, and that is going to cause the uplift from taking place. So uplift of subsidence are related to plate tectonics, but don't necessarily have to be just because of them. It could be because of changes in magma pressure or changes in weight over the crust. But either way, it causes bending of the surface up and down, and therefore the bending and the changing of the rocks in it. The last one I haven't talked about yet are processes which are not related to the core heat. Processes which are more related to the weather and therefore related to the sun, which causes same things like wind and rainfall to happen. The sun is what makes water evaporates, which makes rain in the first place. And you also have gravity here, though, because the gravity is what's going to pull that rain down, and it was going to cause the rivers to flow towards the oceans. Gravity also causes rock slides. All of these things together cause the breakdown of rock into sediments. And there's a whole different content assessment in 7th grade science about that, erosion and weathering, how the weather and the power of the sun and the wind and the gravity and life all cause the rocks to break down. That's right, life, because animals will burrow in rocks and move around the ground and actually cause the rock to break into pieces as well. Erosion and weathering, though, are not necessarily related to the core of the earth. And so that's why they're primarily caused by the sun's power and by gravity, a little bit by life. Which, of course, life is powered by the sun. So ultimately, it's kind of like a lot of it is based on the sun. Related to erosion and weathering, you also have the ideas of deposition, cementation, and compaction. Now, remember, after rocks get eroded, they get carried by the wind and water in rivers and placed somewhere. That's called deposition. And as those sediments get placed on top of each other, they squeeze each other over thousands and thousands of years, causing compaction. And the rock basically squeezes to form new rock. And sometimes the water will also seep between those minerals and actually deposit chemicals which will cause the rock to glue to the sediments to glue to each other. That's called cementation. Together, the placing, compaction, and cementation of sediments creates new rock called sedimentary rock. Of course, since this is related to weather, and the sun is the main energy source behind that, and of course, gravity also matters because rainfall, river flow, rock slides all have to do with gravity. And of course, the squeezing has to do with gravity too. The last process I haven't talked about yet is this idea of things that come from outer space changing the earth. When gravity pulls meteors and comets and they hit the earth, it causes craters on the surface of the earth, which causes indentations, right? And breakdowns of rock. and formation of new rocks because of pressure and heating, such as breccia. Now, this is also obviously crucial to the formation of the surfaces of the Earth. So most of the processes we talked about are in here, geological processes, are actually caused by the core heat itself, and therefore partially because of gravity. But a lot of them don't necessarily have to do with them, especially the ones which are together in the water in the Earth content assessment. By the way, there's also a separate content assessment on plate tectonics and volcanoes, and another content assessment for just plate tectonics and the processes that make the plates move around over thousands of years. So these topics are explored in more detail in separate areas of the curriculum in middle school science. But these are the processes that change the Earth, all right? And in the next video, we're going to talk about how the Earth's rocks undergo chemical and physical changes throughout these processes to actually change the materials that the Earth is made of. I'll see you guys then.